Hey guys, today we are talking about a derivative. And so we started kind of seeing what that was with the secant and the tangent lines yesterday, but now we're going to formally define what a derivative is. And so kind of like that picture that we were looking at yesterday, well, the last time you watched the video, if I have a point x on a graph, I know that the corresponding y value to that point would be f of x. And so let's say I have some curve, perhaps it looks like this, and I wanted to find the average rate of change, then I can use that secant line. And so if I wanted to go, let's say they gave me this distance. Remember, they're going to like to give you the distance away and not necessarily the second x value. So this, if I call this distance h, then I know that that corresponding point right here would be x plus h. And similarly, wow, my graph is pretty small, that function value right there would be f of x plus h. And so again, I can go ahead and I can find that secant line in between those 2 points to find the average rate of change. But if I want to find the rate of change at this point, that's considered the tangent line. So this right here would be my secant line, the average rate of change, whereas the tangent line at that point is the instantaneous rate of change. And that's really what the tangent line represents. It represents the instantaneous rate of change at a point. Now to find the derivative, that's just the slope of that line. So we've got to find the slope right here in order for me to figure out what the derivative of that point is. And so if I look at this, as my secant gets closer and closer and closer to that point, if I kept getting this point, this distance smaller and smaller and smaller away, eventually I would approach that tangent line. And so what we're going to do here is we're going to define this as a limit, because I want this secant line to basically be that tangent line. So this is what a derivative looks like, the limit definition of a derivative. And I just struggled to write an h. So it's the limit as h goes to 0. So as this distance, the horizontal distance, gets smaller and smaller and smaller, and we're going to just have those two y values just like we did with the secant line. And then if you remember on that bottom part there, if I take x plus h, this x value, and subtract x, what that's going to do is my x's are going to cancel and I'm just left with h on the bottom. So this is that definition that you really need to memorize. Well, if I don't like cross out the whole thing, because that is the limit definition of a derivative. So you're just looking as this distance in between your 2 points gets smaller and smaller and smaller, it goes to 0, this limit is going to give you that tangent slope. Okay, so that's the formula. We have a couple different notations for how I can say what a derivative is. The first one that you're going to see a lot is f prime of x. So we saw that inverse notation with to the negative 1 power. This one is f prime of x. Okay, they also might show you dy over dx, that also represents a derivative, or just simply d over dx. Okay, all three of these things are notations for a derivative. So I could have said any of those things are equal to that limit definition. Okay, next thing I'm going to do is we're going to go through a couple little web-based applets that kind of help you see more of what's going on in this. So the first one is going to be finding the derivative at a point. And so this is the website link if you wanted to go visit this on your own time to kind of keep going through it. But basically what this guy is going to show me is my secant line and my tangent line. Oh, nope, except for I picked the wrong one first. Of course I did. Where is that? Okay, I fixed it. So right here, what we see here is this green line right here. This is my secant line. I can see that it's going in between 2 points, and so 2 points is the secant line. Whereas this dotted purpley blue line, that's going to be my tangent line. It's just at 1 point. And I can see here, if I get my points really close to each other, if I get those points almost where the h is 0, so there's no distance in between them, you can see that my tangent line and my secant line are going to eventually be the same. So as x gets, or h goes to 0 right there, my secant and my tangent lines become the same thing. And so that's what that limit definition is telling you. I'm taking some secant line that has a distance in between it, and I'm getting closer and closer and closer and closer to it until I am eventually at that tangent line. Okay, so that's the visual representation of what I couldn't quite show you. Okay, now the next one, that's the graph of the derivative. So again, this is the URL for this if you wanted to visit this on your own time. And what this one does for me is it's actually going to make a graph of what my derivative of this particular graph looks like. So this red graph, that is my original function. And the blue graph it's going to do is going to be the graph of the derivative of this function. And so if I look at this, I can just take my slider and it's going to make this derivative graph. And so the first thing I want you to notice is as we get to the top or bottom of a curve, we have that slope is 0. And that makes sense because if you think about a slope of that horizontal line at the top, that's going to be a Hoy when you did Hoy-Vux, which means it has a slope of 0. So if I look, and apparently this is also a green graph, that graph is going to have my y value be 0. The derivative has a graph of, or a plot of 0 right there. Okay, and that's at the top or at the bottom of a curve. I can see right here too, it's going really, really close, and now it is, well, I can't apparently hit it to 0, but you can get the picture right there. Again, that tangent line right there has a slope of 0, so my derivative graph is going through 0. The other thing to notice on here is as I have a positive slope, as that blue line is positive, my graph is above the x-axis. Whereas where it goes to a negative slope, where my blue line has a negative slope, it's below the x-axis. So I can see that that would be the graph of my derivative. Okay, so let's go through another example. Let me find a good one. So if we look at this graph, this actually is the graph of sine. You can't really tell because there's no tick marks on it, but we know it's starting at the middle and going up. So this is a sine graph. So again, I know if I'm going to be at one of those tops or bottoms of my curves, my derivative should be at 0. So my green line is at 0. And again, at the top, it's still 0 right there. And if you look here, we have that I start out with that negative slope. So I'm below the x-axis, I hit 0. Now I'm above the x-axis, hit 0, and I just keep going. And again, at the tops of curves you have 0, and at the bottoms of curves you have 0. And then we have positive above the x-axis, negative slope below the x-axis. And the really interesting thing here is I have no idea what's going on, but with this blue line. But the really interesting thing here is if you look at this graph, a graph that starts at the top at 1 and then goes down is actually the graph of cosine. And we're going to talk about this more, but it looks like the derivative of the sine graph is the cosine graph. Okay, and I have one more example, actually 2 more examples I want to look at on this. And the first one is this graph of just of a line. And apparently this line is going to be something like y equals 2x. And if I look at this, again, we're thinking about what the slope of that tangent line would be. And so as I drag my slider up, I'm going to see that my blue line, I'm pointing at my screen right now, my blue line is the exact same the whole time because I have the same slope. It's just a line. And so if you look at the graph of your derivative, it also is just a constant. And it has that, it's always at 2. It's telling your slope is always 2. So this linear graph, since it had a positive slope of positive 2, it's going to be up there at 2. If it had a negative slope, if it was going down, it would just be that constant over on the negative side. Okay? And the last one is something that looks like this absolute value. So originally when I thought about limits, the absolute value right here did have a limit because I looked and I came from the same thing on both sides. But the weird part here is how am I supposed to draw a tangent line right there? I don't have a nice smooth curve at that point. And if you look at the graph of your derivative, which again you have the same slope on that side, it's a negative, and then all of a sudden right here there's no way to make that transition very smoothly. All of a sudden it goes from negative to positive, and so we have that jump in the graph. And that jump is going to make my graph what we call non-differentiable. If you have sharp corners, you cannot take the derivative at that point. So if you have a sharp turn like this, where it doesn't gradually turn into the other type of slope, then you have a non-differentiable graph. There's no way for me to find the tangent. Okay, and so again, these are the 2 links if you wanted to pause and write them down so you can kind of play with some more of those graphs. That would be fine. I'm going to go through one algebraic example so we kind of have an idea of what we're looking at. And we're going to practice with this example, with the type of algebraic stuff a little bit more on the second day of derivatives, but just to kind of get you used to this, if they give you a function and they want you to find f prime of x, which is again the derivative, the equation of the function of the tangent line, or if they wanted you to find the derivative at a point, we're going to use that limit definition. And so if you have already lost it in your notes, the limit definition just looks like this. And so it's really going to be similar to what we were doing with the secant line stuff. It's just now we're going to formalize it and put that limit in the front. So this is what my definition looks like. So wherever I have an x in my equation, I'm going to replace it with that x plus h. So when I write this, I'm going to write the limit as h goes to 0. And then again, wherever I have an x in my original equation, I'm putting an x plus h. Quantity squared. And then I'm going to subtract the equation with just a regular x in it. And be careful here, that subtraction is going to trip you up a lot. If you need to, put parentheses around it if it's a function with multiple terms. And then finally, my denominator is just h. And now this is just like what we were doing with limits, where you try to plug in, and you're going to notice you get that indeterminate form. So now I'm going to have to change my equation in some way. And so I'm going to have to actually FOIL out this top part. And then I'm going to have to distribute the 5. I hope you love the sounds of the printer in the math office. Okay, and then something really great happened, and that is that my x's canceled. And so what I notice here is that I have an h in every single term, so I could factor out the h. Which would then make my limit no longer indeterminate, because now if I plug in a 0 wherever I see an h in here, I would have 10x plus 5 times 0, or just 10x. So that would be the derivative of this function. So my derivative is f prime of x would be 10x. Okay, and so that would find me the slope of my tangent line at any point on my graph. So if they want a specific value, like for instance at that point x equals 3, all I got to do is plug it in. So f prime of 3 would just be 10 times 3, or 30. And the other way they could ask that, they could ask you what the instantaneous rate of change is at a certain point, or again they could ask you what f prime or dy dx of 3 is. Okay, and that's all I've got. Again, we'll practice more with the algebra. I just want you to really get what that derivative is. It's the slope of the tangent line at a point.